Great. Welcome back to the third lecture. We were just discussing Weyl's inequality for quadratic polynomials and its applications, why it's useful. It's very useful in the minor arcs, where you have, it's a reflection of the fact that there's a lot of noise on the minor arcs. And one of the themes that's going through here actually is that the major arcs, which have the small denominators, are actually the low frequencies from the point of view of harmonic analysis. And the minor arcs are the high frequencies. There's an actual additional subtlety here where the major arcs, each one of them has also its own notion of low and high frequency, which comes from the Euclidean place. So the minor arcs are really saying that it's high frequencies in an adelic sense, where it's the portion of the adels that have a large denominator. It's basically the large primes. The large primes are playing the role of high frequencies here in the adels, and also the real plays a role in terms of low and high frequencies. So we'll see that as a running theme through this, and we've already seen, in particular, the Weyl's inequality in the minor arcs is one instance of that. And as we process the major arcs in this talk, we'll also see how it's a low and high frequency argument as well. But let's get to actually proving Weyl's inequality. It takes a few steps to do this, and it'll take us some time. I'll restate Weyl's inequality in a bit for quadratic polynomials, but one of the key steps in this is understanding Weyl's inequality for linear polynomials. So there's two stages in proving Weyl's inequality for quadratic polynomials. It's one, prove it for linear polynomials, and two, leverage that information. So let's focus on the first one, and we'll get to how you leverage the information in a bit. What is a linear polynomial? For us, it's just, I have this sort of exponential sum. I take a sum from n equals 1 to r, and I look at e to the 2 pi I nt. The bound we get is it's actually, well, okay, the trivial bound is again just the length of the exponential sum, because each of these is a unit. Its absolute value is 1. So we never want to get a bound worse than that. But you also have another bound here, which depends on t, this parameter affecting our exponential sum. What its value is mod 1. When you think about it in the fundamental domain from -1/2 to 1/2. So I'm identifying R mod z, or the torus, with the fundamental domain from -1/2 to 1/2. And I look at where t lands in there. If t is equal to 0, then this inverse, so the norm on the torus would give that a value of 0. You're close to the origin. And the norm is really how far away are you from the origin in a symmetric way. And when t is 0, the trivial bound is all that you get from here. Right? This bound of the distance to the origin, to the -1, is infinity. And you see over here that this trivial bound of r is actually sharp. It's exactly what you get, right? Because all of those phases are actually 1. So this really is a statement more about what is happening when t is away from 0. And it's telling you that you're going to get some cancellation, depending on how far away t is from 0. Right? So let's prove this. The proof is, well, you have a geometric series that you get to use. And that geometric series is, each one of these is e to the 2 pi I nt, so that's e to the 2 pi I t to the nth power, right? And I just do a geometric series. I get the r plus 1th term. R here is a natural number, and that's just e to the 2 pi I t r plus 1. And then I get, oh, that should have been a 1. Yeah, that should have been a 1 here, sorry. And then you could pull out the factor of e to the t, e to the 2 pi I t, and just be left with something that has on the bottom 1 minus e to the 2 pi I t and 2 units on top. So that when I take the absolute values here, I just say that this numerator is less than or equal to 2. I'm not caring about how much these two are lining up to each other. I'm just going to apply the trivial bound. And really, that means that the denominator looks like this. And it turns out that this is exactly bounded by this norm. That's a little exercise for you to do just to make sure that you understand the norm. And it's possible that I'm wrong here. It's always great possibility that I'm wrong. And if I am, though, there's just some constant here, probably 2, which makes this correct. But a factor of 2 is not something I'm going to care about for error terms.
I highly doubt you're wrong. I mean, the Taylor series for the denominator is like, I mean, the Taylor series for E of t is like 1 plus 2 pi it. So,
right, so there's a pi maybe.
Yeah, it should be 1 over pi, so it should definitely be fine the way you've written it.
Great. I like to think I'm right, but I'm a little biased, so I'm glad to hear someone else agrees. Yeah, so this is a great bound for us. It's super simple to prove. Geometric series, one of the few things we really know how to handle from calculus, right? If you get down to a geometric series, you're golden. But not the golden series. So how do we make use of this? I still haven't said how to prove this for quadratic polynomials. And I'm not going to tell you just yet, but I'm going to say, let's start examining this in a major arc, or not a major arc, sorry, just a fairy arc, because we're going to care about the minor arcs, right? So I impose a condition on t, it's close to some rational, and it's close in the sense that if the rational has no denominator q, remember where a and q are co-prime, then it's close by 1 over q squared. And like c doesn't, oh, I should have left that out. C doesn't play in here. I just look at what sums, how this sum, which is one bound for an individual exponential sum, works on average. And that n here should be an h. This is where I really wish I had a stylus or my pen to correct that. So n here is h. So I'm going to take a sum of these linear Weyl bounds, and I'm going to see what happens on average. Turns out on average, there's a bit of cancellation, or there's a bit of periodicity, really. The trivial bound would be h times r, because I always have this minimum by r, right? If this is much worse than r, then I've discarded it. I just use the trivial bound. Great. That comes up here, h times r, but it turns out that you can actually basically save a factor of q, because there's some hidden periodicity in this exponential sum, in this sum. Sorry. So let's see how that happens. It's not at all obvious, but it's really cool that it's there. Very useful. Great. So just for the moment, let's actually fix our t to be that rational and see where this periodicity is coming in. When we do that, I just replace t with a over q here. Good. And I find out that, okay, this is actually an honestly periodic thing. As h goes from 1 to q, it's the same as it goes from 2 to q. Sorry, q plus 1 to 2q, 2q plus 1 to 3q, and so on. So I break up h into residue classes mod q, and I have h over q possible representatives in each residue class. And for each residue class, I just have this term. So where does this plus 1 come from? This plus 1 comes from rounding, right? If h was actually q squared minus 1, then, or sorry, q squared plus 1, then I have to go all the way to q squared plus q to apply that idea. But that's just making this sum bigger, and therefore if I get an upper bound that's of that shape, I'm fine. Let's do that. We care about what this sum looks like, where I now just care about the modulus q. And, okay, well, when h is equal to q, what's this term? It's just a 1 here. H over q is just 1, and a is an integer. So this thing is 0 to the inverse, and the minimum is actually r. But for all the other terms, I get this expression. Now, the cool observation is a is co-prime to q, and that means that this sum, I can just take the a out, right, by repermuting the values of h. mod q. And now I'm just left with a series that's the sum of h over q inverse, which is q times the sum of 1 over h, as written right here. Pull out that q. I've got sum of 1 over h to q. That's just a log q, as we all know. It's a harmonic series, and we get the bound that I claimed right there. This is just when we're actually at the rational point. The point now, the objective now, is to show that's true in a neighborhood. So how do we extend it to this neighborhood? Well, we actually just, we cut up the torus and use the pigeonhole principle. And we do this in a very precise way. Turns out it's a little fickle, but it's very doable. Okay, again, take the torus. Let's cut it up into intervals of length 1 over q, centered at rational points, b over q. Where b is now, I'm thinking about the torus as being from -1/2 to 1/2, because this norm on the torus is assuming that you defined your point in that range, in that fundamental domain. When I do that and I look at the points b over q, that just means my b is some integer in this range, from -q/2 to q/2. And what's the enemy for us? It's in this sum. When we made this reduction, where we could pull out the a, it's the enemy is that we actually had some conspiracy here where I've replaced a over q with t that really gives me a lot of terms where h is q, or 0 mod q. In which case, then I have to apply I have to take the trivial bound, this big R, over and over again. That's our enemy. Turns out that doesn't happen. Okay, and heuristically, why would you expect this? You'd expect from, say, Kroneker's density theorem, that if I look at the orbit of nt mod 1, where t is an irrational number, right, that becomes dense on the unit circle. Moreover, Weyl's equidistribution theorem says that in any arc, the expectation of landing in the arc is proportional to the size of the arc. But Weyl's inequality actually uses, Weyl's equidistribution theorem actually uses Weyl inequality, so we can't just apply that. This is the actual work to deduce such an equidistribution statement. So what we're going to prove is some weaker version of that actually at the moment. And that weaker version is going to say that basically the h of t we can only have a bad h for any fixed t. There can be at most 3 bad h's. Right? How do we make that precise? So I'm going to introduce a little bit more the intervals, a little bit more notation. I have my unit interval. This is -1/2, 1/2, and I pick my big Q and I cut it up into Q arcs. Arcs of width Q, 1 over Q. Sorry. Okay. Since Q is an integer and this is length 1, of course, these are nice partition. There's no edge effects to worry about. And I can parameterize it by just picking by doing a slight shift and actually just picking this so that I look at each b over q. Right, so this is b over q. And my arcs, or my intervals, are just symmetric about that point. So that the half distance here is 1 over 2q. And I parameterize it as that sort of family. Great. Now we see if h of t, or we're running how as h varies over the interval from 1 to r or 1 to q, how h of t is distributed across this And our enemy is, of course, zero. If I end up landing here too many times, I am in big trouble. That's what I want to avoid. Okay. So the main goal here is to prove that there are at most 3 integers that can land us into any of these intervals, j of b over q. That should be a division rather than a period. And that's at most 3 integers in any window in the integers of width q. Okay. So once we do that, then we know that, say, at least q over 3 intervals have points in them, and you can see just heuristically that what's the worst thing that can happen to you is, all right, I get my 3 points here in the interval around 0. My next 3 points are here in the interval next to it, and this one next to it, and the ones adjacent to those. Because the sum for each point in here, you get a factor of h over q, or actually, sorry, b over q, and then we have parameters. For each point in j of b over q, I pick up a contribution of b over q coming from this. It gets inverted, actually. So that's just, of course, q over b. And then we see that we're going to get another, when we sum up over b, we're going to get something, again, of size q log q. And to make that rigorous, we pad out the actual sum, right? I let n of b over q be the number of h in any interval of length q inside the integers that lands in j of b over q. I know that, or we're going to show that there's at most 3 such possibilities for any b. And now I just overcount, losing a factor of 3 from what I actually expect the truth to be. We do that by, again, just breaking up the sum into residue classes mod q. And over the whole, so I break into periods with respect to q, and I sum over all possible periods. On each period, I have this bound. I use a trivial bound at 0. There should be actually a 3r here. And then I get 3 times 1 over b for all the other things. And again, that latter part right here is just a log q. So that actual bound that we wanted applies. It follows immediately from this. Great. Now our task is to prove that there are most of these 3 bad possibilities. Wonderful. And the way we can do that is we write each h in terms of its residue class. So I'm looking inside of an interval, I'm looking at all the h from qm to q times m plus 1, or qm plus q. And I'm letting r range from 1 to q, or 0 to, from 1 to q is how I chose to do it. And what happens when we look at t in this representation? Well, we throw in a factor that we're going to add in 0, and we're going to add in a nice way. Our condition on t is how close it is to a over q. So we're having written h in this form, we're going to write t as it's how close it is to a over q, and then the contribution coming from a over q. That's what these 2 terms cancel each other out. Now, the first part, we don't know much about at the moment. But the second part turns out to have a bit of cancellation because I chose qm, and it's being offset by a q, or 1 over q. So the term that is just a times m here is an integer, and using this norm on the torus, any integer goes away. And all we're left with is r times a over q minus b over q, or this term right here. Our question is, well, we're trying to bound the number of h lying inside of the interval j of b over q, which is b over q minus 1 over 2q up to plus 1 over 2q. And that's just this statement right here. We want to know when this thing now is less than or equal to 1 over 2q. But here's where our condition comes in to save us. We're pretty close to A over Q by a factor of 1 over Q squared. When I multiply by R, that means I'm within a factor of 1 over Q. And the triangle inequality tells us that this means that Q of MT plus this edge that we had before that we had to worry about is at most 3 over 2Q. From here, we see, all right, Q is fixed, M was fixed, we fixed that window, T was fixed, A and B were fixed as well. R is the only thing that can vary here. And R is varying in an interval from 1 to Q. And when you look at R divided by Q, this expression, there are only 3 times that you can land in any given arc, any given interval. And so N of B over Q is at most 3. That's a little tricky. I'd like to pause for a moment, enjoy a sip of tea, and see if there's anyone had any questions about that, or maybe had a nice quicker way to see it or something like that. I feel like this is the trickiest part of Weyl's inequality, proving this particular N of B over Q is less than or equal to 3 bound, and the rest is very simple things from calculus. It's really, in my view, the heart of why this works. It is a very weak statement about equidistribution of how things are. Or it's not even equidistribution, it's just saying things can't pile up too much. And from there, you can deduce a lot more. For instance, actual equidistribution. Great. Okay, I'll go on since no one has any comments at the moment. But going back to the proof of Weyl's inequality for quadratic polynomials, we still need to figure out how we're going to actually use the linear one and the linear one on average. This extra saving in terms of a factor of Q. So what was the problem that we had? T is close to some rational, closer than 1 over Q squared. And this rational is in reduced form. A is coprime to Q. Q is a fixed modulus. However, C was just some linear term, some linear frequency that was allowed to do whatever it wanted. Now we need to do some operation that is going to be agnostic to what C is. And Weyl had a very clever idea. Weyl said, let's take this exponential sum, take its absolute value, square it, and then shift things and apply the triangle inequality in a way to reduce down to the one-dimensional exponential sum. But it ends up being a average over the linear Weyl inequality. How does that work? I'll take my exponential sum. I write it as a double sum where I've written this one times its conjugate. Right, so I have now an M and an N that go from 1 to R. And so writing it as its conjugate, it turns any positive term into a negative term, right? So I've got M squared minus N squared times T. And I've got M minus N times C. And we actually just write M as N plus H. So it's looking at, you're sort of fixing one of your variables as your reference. And you think about N as the shift. You think about, from that variable, you think about the other one as a shift of it. When you do that, it turns out you're thinking about, you're taking a difference of your polynomial. And that's like taking a derivative. And what it's doing is it's going to be knocking down the degree when we do the triangle inequality in the correct way. You see that coming right up here. So we have C depends only on the shift H. So if I just rewrite my exponential sum, which is currently over 2 variables M and N, as over, say, M and H or N and H, as I'll actually do, then we're going to be able to apply the triangle inequality in terms of H, and it's going to just leave us with something for N. It's still, the N actually has an H component to it, but it washes out. So let's see how it washes out. We start by reconfiguring our domain. I have a bunch of lattice points, or my m and n are in Z2, and they lie in this window from 1 to R. I think it's better to write it as that. Bunch of integer points here. What do? I have m going in this direction, and going in that direction, and I apply a change of variables to the sum. I apply the change of variables by this matrix. That's it. Yeah. Oh, okay. My h and my n look a little bit alike, too much alike. And what effect does that have on this? It ends up making our range of integration actually a rhombus sort of shape. But we're going to still want to sum in terms of vertical lines as I go from left to right. Which means that my sums are getting shorter when I are starting out very short, then they get up to some maximum width, and then they decrease in length again. And I have to, it's not as straightforward here. I get to apply Fubini's theorem right away, but now I've done a change of variables where I don't just get to apply Fubini's theorem. But that is what we're actually going to exploit. Right, we can find the actual points for our region just by a straightforward calculation. I've included it here, but I think this picture is a bit more useful in terms of thinking about how to do that. We are going to break this region up into 3 pieces. I've drawn this a little bit misleadingly. I should have drawn it a bit better so that it's actually like this. And there's one big line in the middle. And then it's getting shorter as you go away from that center line. Now, the center line is the diagonal here, which is when m is equal to n or when h is equal to 0. So this is n in that direction and h in this. Oh, no, sorry, this is h. And that's n. And this is h equals 0. When I do that, I pick out this diagonal because m is equal to n, and our exponential sum is just all a bunch of positive terms. There's cancellation, however, on all the lines parallel to this diagonal, which are all of these shorter ones, vertical lines, under the change of basis. How do we actually pull that off? Right. So I said I'm breaking up my region into 3 pieces. This one plus the right half plus the left half. And on the middle line, all of these terms, h is equal to 0, so that n squared cancels out, and I'm just got t times 0, and then c times 0, which is just 0, so that each of these is a 1. And I've picked up just the length of the sum, r, the trivial bound again, right? But this trivial bound is applied to the square of the maximal function, not maximal, Freudian slip there. I always have those in the back of my mind. It's applied to this exponential sum. It's whereas the rest has a certain symmetry. This half is just the conjugate of this half in terms of the exponential sum. And all we have to study is the real part of this exponential sum right here, because it's just 2 copies due to the conjugacy. And we're going to ignore the real part. We'll just take an absolute value on that sum. We'll take an absolute value on that sum, and then we'll move it in past the h. When we do that, we end up being able to ignore this h squared here. So that's a t times h squared. That comes out as just a phase of, it just gets 1 in the absolute value, and this this c times h also gets normalized to a 1. And all we're left with is this sum. Again, I've been using this notation where this brackets around a number means it's just from 1 to that number, inclusive at the endpoints. Great, and this is exactly what we're looking for with the Weyl bound on average for the linear polynomials. So we just apply that here. And remember, our t was with the t being 1 over, t minus a over q is less than q squared. What we do here is we actually throw the 2 onto the h, so that when q is odd, at least, that doesn't have any effect, because 2 just permutes all the values of h mod q, all the non-zero ones, or the coprime ones. Right? And when h is not, it's a very simple modification of the previous thing to do to just get the bound that we need. Alternatively, you just apply the bound twice, splitting up the factor of 2 into 2 pieces. And there we go. We've gotten the bound that we claim. Oh, where is it? Great. Are there any questions about that? It's a really elegant proof, in my opinion. We see actually that the epsilon here is really a log r as well. Right? And we picked up that factor of 1/2 because of the fact that we have worked with the square. So we take the square root. Great. I'll move on to the principle of non-stationary phase again, if there aren't any questions. I'll give them a minute and just drink a little tea. The next several slides are actually going to be thinking about the continuous versions of those arguments that Weyl just gave. So all the sums are going to be replaced by integrals, or either the sharp cutoff here, or the smooth cutoff here. Now the discerning participant will notice that I actually stated all of my bounds for the sharp cutoff of Weyl's inequality, but the ones that I need have this factor of phi that smooths out the sum for me. It turns out that all you have to do is just keep track of that factor of phi in here, and it doesn't give you, it gives you the same bounds, at least qualitatively. There may be now a factor of 2 that you have to concede, but a factor of 2 is nothing in comparison to this r. It's fixed and it's kosher. So we actually have, let's dive into the continuous versions of these two arguments. Right? Going back to the linear exponential sum becomes now a linear oscillatory integral. And just by integration by parts, or not even integration by parts, actually it is. It's integration by parts here again as well. We find out that this is less than, I should have had a factor of 2 pi. There should be a factor of 2 pi down here. This bound is either at most 1 or 2 over 2 pi c, which is just 1 over pi c. Why is that? It's because I want to say 1. I think I meant to say x. I'm sorry. This should be an x. Why an x? You just apply the triangle inequality and move it in. All the phases in there are just ignored, and you have something of length x. Otherwise, if c, and that's sharp when c is equal to 0, for instance. Otherwise, for c, you end up getting basically 1 over c times e of x, big X, times c, and e of minus e of 0 times c. And again, that's the difference of two things that are units. You just apply the triangle inequality on top, and you just left out with something of size 1 over c. You can do a lot better if you smooth the exponential sum. And that's why we chose to do so before, And we saw how this was useful for us. Just to recall that, maybe a little bit more precise or give something slightly different take on it. Just remember, if phi here, which is not our test function that we took at the beginning, just some Schwartz function. When integration by parts applied to a Schwartz function tells you that the Fourier transform of Schwartz function is also Schwartz. Now for us, we have to consider dilations of these Schwartz functions, right? And what we saw before is that, at least in the one dimension, you pick up something that tells you the length of this integral times some of the cancellation that happens when t times c is really large, or not really large, just bigger than 1. Right? Again, this is just a reflection of the fact that the Schwartz function, Fourier transform of a Schwartz function is a Schwartz function. Now, more generally, the principle of stationary phase tells us that if we have some phase function, psi, say it's C1, and the absolute value of the derivative is always at least 1, you just need always bigger than some fixed constant, but rescaling allows you to do 1, then for everything, so you integrate against your test function, and the principle of non-stationary phase function now tells us that that previous bound actually extends to the same bound for any such psi. Okay. Before, psi was just psi of x was just x, which derivative is 1, and therefore the absolute value is always greater than 1. But now if you have something that's a bit different, it's like a little perturbation of x, then you're going to be doing fine. You still get the same cancellation. And the proof of that is still just integration by parts. But you introduce sort of there's a very nice way to package this. I introduce this differential operator that's going to do the integration by parts for me. And it's in tandem with it is its adjoint operator, defined by D Dagger, which sort of swaps the order in which you're doing things. And all you have to do now in proving something, if you know these two are adjoints, which is a simple computation to just check and apply, then you, to be clear, we're not taking a second. Yeah. Then all you do is you keep moving the operator. You find out that when you apply this operator to, there should be a psi here. When you apply this to e to the c psi of x, then it acts as the identity, because it's exactly pulling out the factor that would, it's normalizing by the factor that would get pulled out. And now you just apply the adjoint version of it. You just move the adjoint version over to it. And this is a Schwartz function. So you get to, you just start calculating derivatives of phi, but the derivatives are being multiplied by psi prime of x. And that is always bigger than 1. So this term is never getting too small, no matter how many times you apply it, this adjoint operator. And so you still get the same bound. Unfortunately now, if you talk about a quadratic phase, which its second derivative is, its first derivative is 2x. So the first derivative of x squared is 2x. That is 0 at x equals 0. So in particular, if we're looking on all of R, or just even the interval from -1 to 1, it doesn't have this nice bounded away from 0 property for principle of non-stationary phase. Then it turns out that you actually get a much worse bound. Then you don't get arbitrary decay. You only get decay of order c to the -1/2 as c goes to infinity. Oh, I have something in the chat. It may be easier not to use integration by parts and just observe that everything cancels out except for at most a single period. But when that happens, you
sorry,
only
that was for the rough.
Yes, for the rough one. Yes.
Yeah, sorry, I was not being clear.
Yeah. Okay, so returning to the principle of stationary phase, so what is this? What is the non-stationary meaning in non-stationary phase was that this first derivative was always bounded away from 0. Say it was always an absolute value at least 1. the stationary part of stationary phase is that the derivative, the first derivative has a 0 somewhere. Okay, it's much smaller than 1. Now, when you have a derivative for your phase function, which in our case is x squared here, it turns out that you get a much worse bound. You only get square root cancellation. So let's prove that for just quadratic polynomials. This is pretty simple to do, and it's a very nice proof as well. You take, all right, we take our phase function psi as x squared. Again, the first derivative, it fails this first derivative test of being never non-zero. Okay, bummer. But that's actually, we only have to worry about that if the function phi that we're starting with in this thing actually includes 0. If it doesn't include 0 in a support, then this function is always bounded away. X squared is always bounded, the derivative of x squared is always bounded away from 0. And we can actually just get the non-stationary phase bound from before. So we only care about when phi is actually containing 0. The supportive phi, I mean. Great. So assume it's in the support, which I'll call I. It's going to be just the smallest interval, actually, that contains the supportive phi. Now, we can't apply a non-stationary phase, but for x squared, there's only one possible 0, and that is at x equals 0. If I'm a bit away from 0, then I can apply non-stationary phase. What I didn't go through in the proof of non-stationary phase is, right, this bound, I gave a uniform bound when this is always at least 1. But if it's just some constant, some small constant, like 1/1,000,000, then that bound is much worse. It depends on the 1/1,000,000. And the bound gets worse as the derivative can become smaller. So what we do is we break this major arc. We break this interval I into 3 pieces. The major arc, or the low frequency bit, where we're containing 0. And then 2 minor arcs, or high frequency pieces, where we're bounded away from 0. And when we're bounded away from 0, we get that psi prime is bounded away from 0 as well. Okay. Now, on that central piece, on that major arc, there's not enough cancellation for us to really get anything good. And so we're just going to apply the trivial bound. I naught has length delta, or sorry, actually 2 delta. And so this trivial bound, when I move in the absolute values, is just at most 2 delta. This is essentially sharp for really small delta, because, especially compared to xc, because this doesn't fluctuate very much. It doesn't oscillate very much. But on the other 2 pieces, we do get to apply non-stationary phase. And we can apply it in the rough form. Now, even though my phi was smooth, this I of L is not smooth. It makes it not smooth. It applies a sharp cutoff here. And when you just do the stationary phase, non-stationary phase bound, it turns out that you get, well, if delta is how close to 0 your first derivative can be, then you end up getting 1/delta times c as your bound. And you get that on each of the 2 minor arcs, or high frequency bits here. And what you do now is you have 2 bounds, delta, 1/delta times c, and you just optimize delta in terms of c. And it turns out the optimal value is, you guessed it, 1/square root of c, so that this whole thing on this whole bound is at most 1/square root of c. Lovely. So we've optimized in the continuous setting what our low and high frequencies are, based on the structure of the quadratic polynomial. Right. Are there any questions up to this point? We are moving on to the next stage. This is completing sort of a lot of what we're talking about Weyl's inequality for the moment. But we're going to make use of these things to process the major arcs. Great. So just before going on to the next thing, one of the other principles in the circle method is really whatever every place matters and every place counts. No pun intended, I guess. This has the effect that if you're going to use some technique in one place, you should try to make sure you use it in every other place, especially if you have a good reason that it's more efficient than another technique you could have chosen in a specific place. So for instance, if I've done something for all the reals, and I'm thinking, okay, on the reals, I'm using integration by parts. Let's go with this, and let's see how we can use that in all the p-adic spaces as well. For us, we actually did the Weyl bounds on the minor arcs, and what we're using here is we're seeing the principle of non-stationary phase as the analogous real phenomena there. So you can actually prove this bound here by also say phi is just a sharp cutoff. You're actually integrating from say A to B here. You can do the Weyl squaring and shifting method that I did before, just for this integral, and get something that looks like c to the epsilon minus a half, as c goes to infinity. If you give me 10 more minutes, I think I can push through to finish this phase of study. The next plan of attack is actually to complete the singular integral. From before, I had shown that all these non-zero frequencies, the n over q that appeared here, were some error term. That was an error term when I was looking at the integral over I of a over q. Now that I've thrown away all those n over q, we just have the 0th frequency to look at. Let's look at what happens on everywhere outside of that arc, I of a over q. When we do that, we get the following bound. Okay. It depends on the size of q and the Ferry level. All right, how do we get that? This is just going to be some calculus. We follow the changes of variables. What ends up happening here is I write out what that Fourier transform is. Remember, it would be e to the 2 pi I x times xc, where xc is just 0, so there's no wave coming into play. It's just this integral now. And when I write out what h of r was, it was just p of x over r times e of x squared times t. And I just move this term inside. I end up getting this expression. I will do a dilational change of variables, sending x to r times x to make this phi function uniform, so that my range of integration here is going to be uniform. That, of course, pulls out a factor of r squared over here. And now for t, I'll just take out that factor of r squared. I will send t to t over r squared. The first x times r of x gave us a factor of r to the d. Now t divided by r squared gave us an overall factor of r to the d minus 2. R was going to be a size square root of n, right? Which is exactly what we were thinking or hoping to get from the Hardy-Littlewood theorem. So we're right on track here. And okay, but that does have an effect of what does this look like? I cut out that interval that's almost symmetric around 0. I have to dilate it by r squared now and study what happens to this. Well, this is where our stationary phase is going to come into hand. Phi is a tensor. It's just, and so is the exponential function. So I actually get that this thing is a product of a bunch of one-dimensional integrals that look like this. There should be a dt, dx, it ran off, I'm sorry. You take the absolute value, moving it in just once, and what you end up getting is you apply the stationary phase bound for quadratic polynomials. So you just get t to the minus d over 2. In each coordinate, we would save a t to the minus 1/2. They're d coordinates. And we do that over this range. Remember, I of a over q was about size, it's roughly going from minus 1 over q of x to 1 over q of x. And so when I cut out r, I cut that interval out of r, basically all of the t's are bigger than 1 over qx. Maybe it's actually 4 over qx, but that's fine. Or 1 over 4qx, but the 4 doesn't care, it doesn't matter. And then just doing some basic arithmetic, you find that you get the bound that I claimed. And that works actually only when the number of dimensions is greater than 2, because I need to be able to integrate this. If d was, say it was equal to 2, then I have 1 over t, and that's a logarithmic blow up. And if d is 1, that's even worse. So as soon as d is 3 or more, you actually get that this integral is integrable, and you're golden. Great. So just rewriting that down, we have this bound for the singular integral. It's the corollary of that, actually. Remember, when I'm outside of I of a over q, I got this term by taking, this will be by taking q equal to 0 or 1. And this other term is going to come from what happens inside I of a over q. Oh, I should have filled in that part, but that's, maybe I'll take just a moment to elaborate on this. What I'm really doing here is I'm taking t and I'm letting it be approximated by 0 or 0 over 1 and plugging that in here. Right, so that q in the previous bound, q times x to the over 2 minus 1 is just a 1 here, and that's this term outside of I of a over q. And inside of I of a over q, I just apply the trivial bound. Right, I of a over q is it's now 0 over 1. So it's basically length 1 over x, and h of the Fourier transform of h of r we saw before was just size r to the d. So nothing fancy there. But we've got to sum this up over all the possible major arcs. And to do that, we have to actually use the Gauss sums. I made the mistake of, this should be g of aq at 0. Now, using the trivial bound for the Gauss sums, I'm not even using the improved bound I got from Weyl. Just using the trivial bound, we obtain a bound of this shape. Because each of these was a size at most q times x to the d over 2 minus 1. And I sum up over q of them, and I lose another factor of y in the process. Great. So up to those error terms, we've actually replaced this oscillatory integral with the full singular integral below. Now you look at that and you see it doesn't depend on the major arc anymore. Like it doesn't depend on a over q or any of these b's or n's that popped up or anything. And it really just depends on n and r. And we are always assuming actually that r is at least square root of n, because we had that to just, we're trying to represent the number of ways to write n as a sum of squares. Our last stage before we do any optimizations is completing the singular series. So we completed the singular integral, now we complete the singular series. And this is where I will actually use the Weyl bound that applied to Gauss sums. The Weyl bound, so remember I was saying that each g of a over q, g of aq, no matter what term is here, is bounded by roughly q to the minus d over 2, but with an epsilon loss, so q to the epsilon minus d over 2. And if you just apply the triangle inequality, I lose a factor of q and a factor of q squared, which turns into a bound of y squared times y to the minus d over 2 plus epsilon. Right, and so when d is at least 4, you only have a size of, say, y to the epsilon. Okay. My point here is that I'm only using some arithmetic at the completing the singular series and in the Weyl bound. At everything else, I've really only very trivially treated anything arithmetically. in the sense that I am, for instance, not caring about what's happening with the Gauss sum. Okay, so another way that I'm trying to express that is by saying that there's a lot you can do by just optimizing things for the real place. You can get a lot of error terms that are good enough for you. So let's see why these error terms are going to be good enough. Oh, here's the proof that I just said out loud. I'll give that a moment before going into why it's good enough. All right, this actually needs just one additional remark on that. This needs d over 2 to be greater than 2 to offset this 1 and to beat like the to beat the harmonic series. So that means d has to be at least 5. And we've seen that condition coming up now in our that was one of the conditions in that Hardy-Little would have. D is at least 5. Okay, let's optimize these parameters now. Things that came up in the proof. I won't go back to each of the slides. I've recorded them all here for us to work with. I always had to assume right at the start that r squared was at least n. My choice of major arcs and minor arcs were such that I was always going to save some power over r for y, and I was going to be a little bit bigger than r to the first power for x. But while I wrote everything down for delta 1 equal to delta 2, I didn't actually have to let them be the same delta. Right? All I had to do was take the minimum of the delta in any of the arguments. Now, for one of the error terms, for instance, the Weyl inequality, we had to show that we are something a bit smaller than n to the d over 2 minus 1, because that's what our main term is supposed to be. And that is actually coming from the minimum of these two. And then when you complete the singular integral on the major arcs, I needed this condition. I needed y and x to be compared to n in this way. And then when I completed the singular series, I needed this condition. And my use of less than here is I'm reading this sort of as much less than, where I'm saving some power in terms of n or r equivalently. Right. We're going to need to take r to be the smallest possible value. That's pretty clear. Just take it to be square root of n. Let's skip the second condition and just see where the third condition gets us. We need this following linear relation, which is the same as saying that delta should be smaller than 1 minus 4 over d. And we're seeing again, this needs to be something smaller than 1 itself. So we're seeing again that d needs to be at least 5. The fourth bound is actually pretty bad for us because I didn't use any of the arithmetic or cancellation coming into Gauss sums. And you could immediately improve it, but instead we see we need something that's been cut off. It'll come up here. We need this. Delta needs to be bigger than 2 over 3d plus 2 squared. If I optimize things so that x and y satisfy these bounds. Oh, there should be a less than here. And you just do that optimization. You pick any delta in this range. When d is at least 5, this term is much smaller than that term. So you have a whole bunch of deltas you can choose. And what we've done is we've shown that all of our error terms are smaller than we expect our main term to be. Whereas at this stage, we have not proved our main term is of the size we claim it to be. But that's what we'll do next time, or we'll start to do that next time. Great, so that's all I have for now. Are there any questions? I'll stop sharing now in case there are some other questions.